Hi there, welcome back to Calculus of Variations. In this snippet we're going to look at Taylor's theorem. Now let's take an example of someone using a calculator. If you wanted to find out what the value of the sine of an angle theta was in a calculator, well, if we had a triangle there and we call that y, and x, and call that r, and we call the angle there theta, and we know that sine of theta equals y upon r. Now if you're going to do this in a calculator, you would find the value for theta, you would stick in your calculator, you press the sign, and you would get a number which would be this ratio here. Now if your calculator can do calculations up to say 15 decimal places, then if we were doing this, let's imagine we were doing it in degrees, then for each one single degree you would have 1 times 10 to the 15 possible outcomes. So that is, so say let's say we need 1 terabyte, right, so of data, okay, and be a byte for each number. So 1 terabyte of data required, okay, just to get 1 degree. So if we had 90 degrees, we'd have 90 times 10 to the 15, so we would have 90 terabytes of space would be required in your calculator. Now that's not feasible, and that's obviously not the way that it's done. So the way that it's done is that your calculator runs through an algorithm. Now that algorithm represents this sine theta. So in one sense, sine theta can be described as being a complicated function. Okay, it's complicated in the sense that if we didn't use any other mathematics, we would have to use a lookup table to find out the value of the sine of theta for every single angle. Now what we want to do is we want to make an approximation to this complicated function using a series of simpler functions. So what does that look like? Well, we want, let's say our take sine x as our generalized function, we'll call it for a general function f of x. Okay, now what we really want to do is we want to make that function there equal to something that's simple. So what are the most simple forms of mathematics or arithmetic? Well, it's going to be add, subtract, multiply and divide. So multiply and divide is different forms of adding and subtracting is just like adding, okay? You're adding a negative. So the simplest form is just a plus sign. So you want to have a simple function, which is a function here, a simple function here, plus something else, plus something else, plus something else, okay, and here. Now we don't know what these somethings are, and that's what we're having to try and decide. So let's go back and let's draw out a function. Let's draw out a function. Remember, we're just talking about random functions here, so let's draw out a function like that, okay, and we call that y, and we call that x. Now actually I'll do it at 0 actually, just to keep it simple. it down right. Okay, so we're going to do the function at 0, draw it like that. Okay, again y, x. Now we've got a function f of x here, which we're trying to approximate using, let's say, another function, which is, I should actually, that's the new function. That's the function that we're using to approximate the function f of x. Okay, so the new function is going to look like that. Okay, it's of that form. So we'll just give that new function of a name. We'll call it g of x. So this is a function f of x, which we're trying to approximate. Okay, we're trying to approximate it using a new function called g of x, and g of x has got, it looks like this form here. It's something plus something plus something. Each time you add something on, you want to get closer and closer to the value of f of x. So let's imagine we look at f of 0. Okay, so when x equals 0, f of 0 is that height there. Okay, so that there is the height f of 0. So if we make a first approximation, really what we would like to do is we would like to make the first guess at it to be the actual value at that point 0. So we want an f of 0 to equal g of 0. Now all we're really doing there then is we're saying we'll approximate this function using a straight line that goes through that point. So there's a point there. That's a straight line that goes through that point there. Okay, so that there is our first approximation to this function. Imagine that continues down like that. Okay, that's our first approximation to that function. Now, it's a good approximation at x0. In fact, it's exactly correct at x0. So we're off to a good start. But as you move further along here, you start getting errors. Okay, so that point there is not very close to that point there, and go back that way as well. And that point there is not very close to that point there. So it's only correct in a very, very local area. So we could provide another approximation. You could say, let's look at the rate of change of the function at 0, and we'll make the rate of change, so that's the rate of change of the function we're trying to approximate. So we find that rate of change and we say, well, we'll draw a line again, but it won't have that gradient. The gradient it'll have will be the same as the gradient at that point there. So let's do that. So if we try and draw that in, so now our approximation looks like that. Okay, alright, that's our approximation. So now it's still a linear approximation. Okay, so but the gradient at that point there is the same as the gradient for our curve here, which we're trying to approximate. So we would want f derivative at 0 to equal g derivative at 0. Okay, and you can see that then that hugs the curve better than the straight line, because the error here was that full distance there. Okay, now the error is only that distance there, or at that point the error was that full distance there. Now the error is only that distance there. So we're getting closer. Now this is where we have to start making a decision, because we could then say, well, let's make the curvature, if we call the f double derivative of 0 the curvature of that function f of x, to equal the curvature g double derivative at 0. So we want that to equal the curvature of this function g, but so you would end up with not a straight line like that, not a straight line like that, but a curve that would come in here and it would come up here, and the curve would come up here and it would hug that curve a bit better. Okay, so that the error wouldn't be that error there or that error there, it would just be the smaller error there. But we're still left with a question, is that we have to choose what curves we're actually going to work with. Now there's different ways of doing it, but the way that we're doing it here is called Taylor's theorem, and he uses a family of curves, or the theorem uses a family of curves known as monomial curves. Now these curves that we're going to use can be written as a family of curves of the form an x to the n. Okay, so for example, when n is 0, we would have a0 x to the 0, right, and then when n was 1, it would be a1x, and that would be a2x squared plus blah 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 plus an x to the n. So now we're going to use g of x, which is the function we're going to use to approximate f of x, is going to be of that form there. Okay, and you can see that that works out for our first two guesses that we had. The first guess was that we're going to guess at just the actual value a0, which is just the height here, and the second guess was the rate of change of the function, which is just a line along here, and the rate of change is just the gradient a1. So that one section there, if you look at it, is a linear approximation which just looks like the equation of a line. That's y, for example, it would be like y equals mx plus c, which is the equation of a line. But now we're going to add in these other factors as well. So we have to make this, we want to make this equal to that equal to that, and that equal to that. But what we could do is we could actually do these differentiations, okay, and set them to 0, and then we can, from that, we can find out what these values of an actually are. So let's do this. So we'll look at g of 0 is just going to be equal to, well, everywhere you see an x you put a 0 in, so all of these x's, they're all zeros, you're just ending up with a0. Okay, so g derivative of 0, well, when we differentiate this once, you'll end up with the a0 disappears as a constant. That will be a1, okay, and that will be 2a2x, and the rest of them will have, that will be nex to the n minus 1. So all of the rest of these here will have a value of x in, and when we put 0 in for x, all of these will disappear. The only one you'll be left with is the value a1. Okay, and if you went in and you did g double derivative of 0, again, once that's differentiated twice, that's just a constant, that would be a constant. This here would be 2a2, and it's been differentiated twice, so the value of x would disappear, and all these other x would disappear whenever we set the x to 0. So you'd end up with 2a2. If you're unsure, just work through a full table and you'll see that these are the values that will come out. So if you put in g, we'll put in 3, just representing the third derivative of 0, you would have 6a3 and g4 of 0 would equal 24a4, and in a general term gn of 0 would equal n factorial, because that's what n factorial is, a to the n. So that would be, n factorial there would be 4 times 3 times 2, which is 24, and that would be 3 times 2, and that would be 2 times 1. So we're wanting to make sure that each of these terms equals our function that we're trying to approximate at f of 0, f derivative of 0, f double derivative at 0, f3 0, f4 0, fn at 0. So from there we can say that our function that we're looking for, that's our function g of x, which approximates the complicated function f of x, can be written as g of x is going to equal, well, it's going to equal the complicated function, the nth derivative of it at 0, divided by n factorial. That would give us our values for an. All we've done is taken the n factorial down. So that gives us our values for our an. So we can plug our values for our an, which is this here, back into our functions here. Okay, so all we'd be doing is we would be multiplying our values for an, that's them there, by x to the power of n. Okay, so you would just have that x to the n, and you would be summing all of those up. Okay, be summing all of those up from n equals 0 to some value, it's your choice what it is, some value I. Okay, so this here then is the function. Now this is the algorithm in effect that we can use in order to create a simplified version of a more complex function. Now that there is called the Taylor polynomial. It's actually I think it's actually Mcgowan. Well, it's a Taylor polynomial fixed at the origin. Now we could make that more general if we write it in the form. We could write g of x equals the sum from say n equals some 0 value 0 to some value I of f of n, not at 0 but at some arbitrary point, let's say x0, times x minus x0 to the n upon n factorial. That there is actually, that's the Taylor polynomial. Okay, now that'll do that for this video. On the next video we'll just go through an example using this, and I think from examples it becomes a little bit clearer. And the reason for going through and doing this is that this is a good way of introducing some of the more complicated areas of calculus of variations. Okay, thank you for listening. Goodbye.